is everybody today? Glad y'all are here, but okay, we are recording. Let me start from the current slide, even though we'll come back to this in a minute. Let me say this first. Hopefully the others will listen when they get a chance to. In this, of course, one of my best classes ever. I have, you are the best class about getting papers in. The research paper from 1, 2, 3, 4, 5 of the 7 are in. So just missing 2. You might know one of them, okay? All right, remind him. Okay, first test. 1, 2, 3, 4, 5. 6 out of 7 have turned that in. Of course, I'm preaching to the choir now because y'all have turned yours in. Test 2, 5 out of 7 have turned theirs in. And again, I'm preaching to the choir because both of you have turned yours in. So y'all are up to date. No wonder y'all are here all the time. Okay, but I just want to let the others know they need to get their stuff in because I want to return all those papers to you on Wednesday, but I can't return anything that hasn't been turned in. So anyway. All right, we're going to come back to this slide later, and maybe even that one, and we're going to do example 3 from chapter 7, applications of integration, 7.7 fluid pressures and fluid forces, and that's going to be, we'll do that right here if I can get my pen set up. Here we go. Okay. Any questions on anything so far? All right. Now, just a little bit. We've already talked a little bit about the test that I gave you last time. Technically, it's due in Wednesday, but if you need more time, you can have it. Because on Wednesday, I'll also be giving you whatever we've covered in the next chapter. You know, what we covered today and Wednesday in chapter 8. That will be your last test. It will be short. Hopefully, it'll be fairly sweet. Okay? So try to, and so finish the test I gave you last time and this one and get them into me sometime next week. Are any of you graduating this term? You are. Okay, that means I have to have yours, I believe it, by Wednesday morning first thing, not 11:59 Wednesday morning, because I believe, I'm not certain, but I believe your grades are due in 12 noon on Wednesday. So if you can get me stuff by, have you heard otherwise? Yeah, I can't remember it. I'm going by memory, and I don't remember where I saw it. Probably was an email, or I may have heard it, you know, but I believe they're due by 12 noon. It may be end of the business on Wednesday, so that would give you a little more time. But see if you can, if you got it anywhere, let me know. And I meant to say this in our first class, but they were so focused on the test, I didn't bother them with it. Have y'all seen anything about the student course evaluations? That should have come out. Yeah, okay. So please do those soon as you can. You can wait till after you've seen and finished the final or seen your grades, but just don't forget. I know when I was a student, at the end of finals week, I shut the brain down and walked out and would, if I hadn't done something, I would have forgotten about it. So please don't forget about it. Please do the student course evaluations. All right, let's do example 3 on page 508, chapter 7, applications of integration, 7.7 fluid pressures and fluid surfaces. A circular observation window at a seawater aquarium has a radius of 1 foot. Okay? And the center of the window is 8 feet below the water level, shown as in that figure there. We don't have a copy of it. What is the fluid force on the window? Okay? So here we have, and here's how they've chosen to set up their axes. There, yes? Oh, on Tuesday. Now that's when our grades are due to you, or yours is due to us.
I guess y'all got to be put in the system because they sent one of those
So that's Tuesday of next week, finals week. Okay. So you heard it from the chapter. I was thinking it was Wednesday. So you have to, if you can get it to me by Tuesday morning, first thing, I can get the grades done by Tuesday noon. Okay. Extra day early. Glad you told me. I don't think I said anything to the first class, but I've got another day or two to talk with them. So, all right. I don't think any of them are graduating this term. That's okay. All right. How they set up their deal here was one, and one. I think it was a 1 foot radius, okay. Then 2, 3, 4, 5, 6, 7, 8. Somewhere up there is the surface of the water, okay? 8 feet up, okay? Here is the window down here at the bottom of the 8 feet, okay? It's asking for what is the fluid force on the window, okay? So obviously we're going to do little strips like this, okay, as they show in the picture there. So we're going to be doing dy's. So our integral that we're going to ultimately do is going to have dy's. And where are they going from? And here's DeMarcus. Choosing not to write well today. Just a couple things. Let me repeat this in case you don't go back and listen to this. I want to return all the tests to people. I can't return your research paper, but all tests on Wednesday morning. So if you can get any back tests that you haven't completed into me by Wednesday, I'd certainly appreciate that. Are you graduating this term? No. Okay. That just found out. I was thinking grades were due by noon on Wednesday. They're due by noon on Tuesday. So if you were graduating, you would have to have your last test in. Thank you. Put this where it belongs. Otherwise, I don't find them later when I need them. Okay. Okay. This is example 3 from chapter 7, section 7.7. See why I have 7s on my mind. So since we're doing dy's, the center of this window is 8 feet down. But the pressure will go to 1 more foot. So we're going to be integrating from 7 to 9. Because we've got dy's there. And the top is 0. So this is 7 down before you hit the top. So it'll be going from 7 to 9. Okay. Now, we want the force on the window. Anyone see something we can use to our advantage here? Oh, and we're doing dy, so we've got to express this length here in terms of y, not in terms of x. Okay? So what do we know about the circle here? Radius of 1. So what can you tell me? What is the center down here of that circle? 0. Remember, this is the y-axis. Well, your height 0, 0. It is 0, 0. But it's 8 feet down. Okay. Oh, yeah. Well, then why did you let me write 7 to 9? Okay? That should be from -1 to 1. Shouldn't it? Well, don't you doing that. Keep me in line. Okay. From -1 to 1 is where we're integrating. Okay. Now, since that's why they chose the origin down here is my guess. It makes this part easier. And what you just said is radius 1. What can you tell me about the equation that describes that circle then? Well, if that were true, it might be that, but it's not true. It's x squared plus y squared equal 1 squared, which is 1, right? Everywhere on that circle, the radius is 1, and so whatever x you have here, y you have there, x squared plus y squared is 1. Whatever x you have here, y you have there, x squared plus y squared is equal to 1, because it's a circle of radius 1. So therefore, we can rewrite that as y squared is equal to 1 minus x squared, and y is equal to the square root of 1 minus x squared. Now, I said that, but I really should be plus or minus the square root of 1 minus x squared. But guess what I want to do? I want to calculate the force only on half of that rectangle, because it's the same on this side, right? They're at the same depth. So I'm just going to double that. So I'm going to leave it to plus. Okay? Otherwise, the length would be from, actually, it really doesn't matter. It's either twice this is the length of this, or twice half of that. Say that again. It'll either be going from minus this to this, which would be this minus a minus would be plus, so it'd be twice that, or I go from 0 to that value and double it, which is exactly the same type thing. Okay? So it really doesn't matter which way you do it. I like doing the doubling. So anyway, let's see what we've got here. Okay. Notice they say seawater aquarium. That means something here. 8 feet below is shown here. What is the fluid force on the window? All right. So this gives us the length. So let me just say, let's just call that L is equal to 2 square root of 1 minus x squared. Okay? And we're not going to double it. We're just going to do that. That's going to be the length of that. There's the width of it. So that gives us the area. Okay? Now, to get fluid force, remember our expressions from before. Fluid force exerted by a fluid is the weight density times the integral from C to D, in this case -1 to 1, and then you need an h of y is the depth of the fluid. Okay, depth. Now what's your depth in this case?
8 feet or 9.
Okay, 8 feet would be at the center, okay, but that's where y is equal to 0, so it must be 8. So the depth, which they're calling h for some reason rather than depth, that is going to be 8 minus y. When y is 0, that would be 8. When y is 1, it would be 7. When y is -1, that would be 9, right? So that covers it. So there's your depth thing is 8 minus y, okay? Your length is going to be twice, I'll put the 2 out front, the square root of 1 minus x squared. And then, so that gives you a length, a depth, a length, and a width. Okay? 3 dimensions, that gives you cubic, what were these measured anyway? Feet. Okay? This gives you cubic feet. Okay? And to get the total force, you need to multiply by the density, which is weight per cubic feet, and that's why they have that in there in front. Now, this is salt water, okay? Remember that? If you turn back a few pages to page 505, you'll see seawater has a density of 64.0 pounds per cubic feet. So that better be the one, yeah, that's the one they use. So we'll put that out front with this, 64. That should be our integral. All right. Oh my. How do we do that? Oops. I said this backwards. Sorry about that. What are y'all doing today? You're letting me get away with way too much stuff. Okay. We want x in terms of y. I kept thinking that and saying, what's wrong with this picture? X squared is equal to 1 minus y squared, so x is equal to the square root of 1 minus y squared, because we want everything in terms of y, not in x. That makes no sense there. Okay. Now maybe we can get going on something here. Okay. How are we going to solve that integral? Okay.
First, would you try to get rid of things on the outside, like 64 times 2?
Okay, say this one more time.
I said, first, would you get rid of things on the outside, like 64 times 2, like multiply those?
Yeah, you can certainly do that. Yeah, that would be 128 outside. Integral from -1 to 1. Now, I would definitely rewrite this as 8 minus y. Make sure they've done it right. Yes. Okay. And they don't do this, but I don't know why. I'm going to do it anyway. 1 minus y squared to the 1/2 power dy. Now, that may not help in this problem at all, okay? Because they're going to do a little sleight of hand for you here. And I'm sure what they're doing is correct, but it doesn't quite seem like it should be, but it is. Okay. They really do pull some slick ones here. Okay. And rather than belabor, because we really need to move on, what they do, they break this into 2 pieces. Okay? 128 is out front for both pieces. So let me just get this done like this. From -1 to 1 of 8 times 1 minus y squared to the 1/2. Okay? Plus, no minus, and all this is inside the parentheses there, y times 1 minus y squared to the 1/2. Both of those have dy's with them, by the way. Okay. Now here's what their argument is. And it is true, but I don't know if you would have recognized it. I know I didn't immediately pounce on it, and I'm still sort of struggling to make sure they're correct on it. But since they're saying it, this is an odd function. Y to the first, and this thing is to the second power here, with 1/2 power there, so that's like it's to the first, okay? Okay, which means that this is an even function, I think, but, no, I'm sorry. They're saying it's an odd function. Second integral because the integrand is odd and limits are symmetric with respect to the origin. They're saying this is 0. I did limits in there. -1 to 1. I probably should just go and skip this problem altogether. Okay? And the reason is that I want to skip it is we haven't done the technique. We're going to do it in the next chapter how you solve something like this. Okay? And they just say, because this is an odd function, which that's not completely clear to me, it is an odd function, the integrand is 0. Okay? So they just throw that away. Actually, we have done that. We've done substitution, so I think we could do that and prove it to ourselves.
Yeah, because that's why would they put something that's in the next chapter, in this chapter?
Yeah, but no, substitution will work here. Okay? So let's do a substitution. Now, it won't work up here. Okay? And they do something else kind of bizarre up here, but it's perfectly correct and legal, and that we can't argue with. I mean, we can deal with. So let's do this one first. Pull the 8 out front, and that'll be 8 times 128. So I'm going to put the 8 out here with the 128. And then what you have, and here's where the sleight of hand comes into play, we're integrating half of a circle. Okay? Basically this right here. Well, we know the area of half of the circle, don't we? Okay? That is
2 times pi radius squared divided by 2.
okay. It's pi r squared divided by 2. The area of a circle is pi r squared. So that's how they're getting around that. That would require a technique we haven't done before. So that would be pi r squared over 2. Okay? So, and the pi here, and the r is 1. So basically, the over 2 is going to make this 4. Okay? So that's going to be 4 times 128 times pi, and the radius is 1. Okay? So that's your answer, okay? And what does that multiply to be? 32, 8, 11, 512 pi. Okay. Yeah. Now, that's their answer. Let's go back and see if we can rationalize why they said this is 0. Well, let's do a substitution. Let u equal 1 minus y squared. Wouldn't that be right? Okay, then what is du?
2y.
Minus 2y dy. Okay? So, what I'm going to do here, because we've separated these completely, let me put this back in, the minus 128 out front here, okay, because that was left over. The 8 came from the other part. This is just that part, okay. So we don't want We don't have in here a 2y dy. We have a just y dy. So let's divide everything by minus 2. Would that be okay? All right. So now that's y dy is minus 1/2 du. All right. We're running out of room rapidly. Okay. So this will be u to the 1/2 du with a minus, but the minus is going to wipe out that minus, so that's going to be a plus. The 1/2 is going to make that a 64. Got it? Okay. And we need to change our limits. Okay. If y is going from minus 1 to 1, what is 1 minus 1 squared? No? Yeah. Okay, what's minus 1 squared?
1.
Okay, 1 minus 1 is 0. And when you do the other one, y is equal to 1. 1 squared is 1. 1 minus 1 is 0. Everything goes to 0. So we didn't even have to show that goes to 0 from our substitution. And that was a legal substitution. Everything's fine. That does go to 0. So all this goes to 0. Okay. So we have shown it. And so our 512 pi, multiply pi times 512, that's, they say 1608.5 pounds. So it's about 1608.5 pounds. Now, I don't see how they can get 5 digits of precision from something that we probably don't have more than a couple. I'd say on the order of 1,600 pounds. That's how I believe it. Anyway, that finishes that. So homework exercises here, if you need to do them. 3 or 5, they're both at calcchat.com. 3 is at calcview. Do 7 is at calcchat. Any of the odds, 9 through 13, they're all at calcchat. 13's at calcview. 15 or 17, they're both at calcchat. 15's at calcview. Any of the odds, 19 to 20, or either 19 or 21, they're both at calcchat. 23 is at calcchat. You can look into doing 25 or 27. Think about doing 27 anyway. They should both be at calcchat. If they're not, don't worry about them. 29 and or 30. Well, let me just say any of the odds 29 through 35. And they should all be at calcchat. If you need more exercises to do when you're working on the test, any of the odd number review exercises would be fine. They should all be at calcchat. Okay? And they break them apart there, but they don't give the section numbers, but you can probably pick out those. There is a problem solving, PS, postscript problem solving, and they say those odd numbers also are at calcchat. You don't have to do those. If you want it to, you can. Okay? Let's move now to chapter 8. Okay? Any questions on this one? That was a little bit of a bizarre problem, but it did work out pretty well. Okay? All right. Let me clear what we've got here. Okay? And we'll go back to, in chapter 8, basically, I apologize for this. This is probably just about the most important chapter in the thing, and we now have 2 days to do it. So we're going to do as much as we can, but as thoroughly as we can. So let's get going on it. Integration techniques and improper integrals. We're not going to do the improper integral part, I'll tell you that. Okay, basic integration rules is 8.1. Okay? We'll review procedures for fitting the integrand to one of the basic integration rules. And what are those? Fitting integrand to basic integration rules. Okay. Here they are. Okay, if you got your text, they're on the left-hand side, kind of the margin type area of page 516. Is that the page you're missing?
Yes, sir.
Okay. That's an important page. Daniel's here. And my pen is not liking to write today. I don't know why. Okay. So I'm missing Vince, Charles, and Jordan. Okay. All right. So here are the basic integration rules. Constant times a function, the integral of a constant times functions is a constant times the integral of the function. We just did that on the last example. The integral of a sum or difference of two functions is the sum or difference of the integrals of those two functions. Okay, we actually did that one on the last problem too. The integral of du is just u plus c. Now these are indefinite integrals, so we're always going to have plus c's in them. The power rule, the integral of u to the n, is going to be bump up the power by 1 and divide by that same number. Okay, that works as long as n is not equal to -1. If n is equal to -1, what's that? It's this one. The integral of du over u is what? Log, exactly. Natural log of absolute value of u plus c. Okay? And then our favorite of all time, the integral of e to u du is e to the u plus c. And similarly, the integral of a to the u du is a to u, but then you have to divide by the natural log of a plus c. Integral of sine, okay, integral of sine minus cosine, because the derivative of sine is cosine integral, and derivative of cosine is minus sine, so the antiderivative has to have the minus there, but the antiderivative of cosine would then be sine because of the reverse of that, so that's sine. The integral of tangent u is, this one you might not remember, minus the log of cosine u, okay? But if you rewrite this as sine u over cosine u, then you see that has to be the case. Okay, that one you can look up. Okay, the integral of cotangent u, which we seldom do, but if you did, it's just like this one, but without the minus sign. Okay, integral of secant u, we've done this one before. It's the log of secant u plus tangent u. Okay. So notice sines and cosine, when you integrate, you just get the reverse. That makes sense. But the other trig functions are going to give you logs, okay? You can kind of remember them that way. And sometimes they're plus and minus. Look them up. Don't try to memorize, okay? Integral of secant squared, well, that one's not as bad because the derivative of tangent is secant squared, so that just gives you tangent u. Cosecant squared would be minus cotangent u. Okay. Now, secant u tangent u, because the derivative of secant is secant u tangent u, this is just secant u, and that would be minus cosecant u. Okay. Now, these are not ones I typically memorize either. Okay. But inverse trig functions, this is how they come out. And notice here we don't deal with inverse cosine, cotangent, or cosecant. We just deal with the, not the cofunctions, just the functions. And again, look these up if you need them. I don't recommend memorizing those. Okay. But those are the basic integration rules. Okay? Now, that in mind, and by the way, let me back up because Daniel just came in. Again, are you graduating this term? No. Okay. I need, okay, certainly research papers have to be in maybe preaching to the choir here, this week, or else you start losing points. But also, I need in all of your tests by Wednesday morning. Okay? Okay. And then I'll be giving you your final exam. Now, the test I gave you last week, if you don't finish that by Wednesday morning, that's okay. Just turn it in when you turn in the final. Because that you only had last week, since Wednesday to do that. Were you here to get that?
Yes.
You did. Okay, good. Everybody got that one, right? Okay. All right. Then, I think we're ready to move to example 1. Yeah. Find each integral. And frankly, you can use whatever you need. Look at those integration rules that you have right there. Does A look like any of those? It's not exact, but anywhere close to any of them. Way down near the bottom.
Oh, yeah. Number 18.
19. You see?
Oh, yeah. The square.
Okay.
There's 2 squares and both.
Say again?
I said there's 2 squares.
Yes. Okay. So, you just have a 4 up top that you think, why do we have a 4 up there? Well, pull it outside. Okay. So this would then be 4 times the integral of dx over x squared plus 3 squared. Right? See that? Okay. Now, looking at number 19 then, that is, I'm sorry, let me rewrite it this way just so it'll be a little clearer. Dx over 3 squared plus x squared. Does that make it a little clearer? Okay. Du, that could be x, over a squared, that would be 3 squared. A would be 3, and u would be x. Okay. So what is your answer? Remember, you got the 4 on the outside, over, the answer is 1 over a, which is, a is 3. Arc tangent, I like to write it as inverse tangent. Okay. U over a, where your u here is x, and the a is 3. Okay. Plus c. Agreed or not? Yay or nay?
I'm not offended by that.
What's that?
I'm not offended by that.
You know what?
Not offended by it.
Oh, okay, good. Okay, because if you look at the other side, the a is it's a squared. That's why I changed the 9 to 3 squared, and then you just plug each other, remembering the 4's on top there in front of it. Okay, now this looks a lot like it, but it's very different, isn't it? Because that x is there. What could you do for that?
Well,
Again?
I was thinking about going up to x, but no.
Pulling it outside the integral? That's what you're integrating with respect to.
Okay.
If you pull constants out, you can't pull the variable out if you're integrating with respect to that. So you can pull the 4 out, which is not a bad idea, perhaps. But what can we do then? Our good old favorite. We did in the last problem that we did.
Substitution?
Substitution. Remember? What would you let be u? X squared plus 9. That's an ugly 9, isn't it? Then, I didn't write a u down. Let u equal x squared plus 9, then du is equal to 2x dx. Well, we have a 4x. So basically what we do, we bring the 2 on the outside from this, and that leaves us the integral of 2x, which is du over u, isn't it? Isn't that all we have left in there? And what's that? Antiderivative of du over u. You gave it to me just moments ago. Or look at number 5. Yeah. What is it?
Oh, yeah, log of,
Natural log of absolute value u. Okay? Which, and you can say plus c, but now we need to plug back in as 2 times the natural log of x squared plus 9. And guess what? X squared plus 9 can never be negative, right? So you can lose that absolute value bars plus c. Okay? How about this one? What can we do with that?
We have to do something with the x squares in the numerator and denominator? Or?
Okay, that's a good observation. You have x squareds in both numerator and denominator. Now, if these were reversed, flipped over, then it would be a pretty easy thing you could do. But with them in this order, it's not quite so obvious what we do. Okay? I know what my first tendency is. I don't know if I should resist that tendency or not. Trying to think if there's any easier way. Yeah, okay. Now, my first tendency should have been slightly different. Anytime you have an improper fraction here, divide. And this is improper. This was proper. That's proper. You can't divide there. This one you can. So this is what I should have seen to begin with. You do x squared plus 9 divided into 4x squared. Okay?
and it's improper because
Because,
squared over.
okay, x squared over x squared is, the numerator and denominator have the same degree. Okay? If the numerator is greater than or equal to the degree of the denominator, that's called improper. Yeah. And these, they're less. 0 over 2, 1 over 2. Okay. Here, 2 over 2, that's improper. So divide. So x squared will go into 4x squared how many times? 4 times. Then we multiply, and that gives us 4x squared plus 36. Right? Right? Okay. Now, I like to just say this, change signs and add. Okay? And that's going to make that a minus, and this a minus. Okay? And when you add those, that goes away, and this will be a minus 36. So it'd be 4 minus 36 over x squared plus 9. Right? Written with the remainder over the divisor. Remember, we used to do that. All right. So we break this integral into the integral of 4 dx. That's the first part. Minus the integral, and I'm going to pull out the 36 if that's okay, of dx over x squared plus 9. Okay. Now that bottom, well, okay. First, what's the integral of 4 dx?
0 or 1?
Okay. If you pull the 4 out here, it's still not. Huh? X. Okay, so this will be 4x. Okay, minus 36. And what would be that integral? Hint. Look up here. Like right here. Dx over 3 squared plus x squared. That would be I'm running out of room at the bottom, so I think I'm going to move it if that's okay. Sorry about this. I should have looked ahead. Okay. Can't get that to come back. So this is going to be 4x minus 36 is in the numerator, and I'm going to rewrite this as dx over 3 squared plus x squared. Okay? Integral of that is 1 over a, which in this case is 3 again, like it was before. So it's a 36 over 3, which is 12 inverse tangent of x over 3 plus c. Okay. Rather a strange one, but certainly things we could do. Divide first, then do it, and use the inverse tangent for that one. This is just straight integration. Okay. So that should be what they got. Yeah, 4x minus 12 inverse tangent x over 3 plus c. It says, note in example 3, some algebra is required before applying any of the integration rules. Yes, yes, now you tell us. Okay. Now, let's first see how they do them, because we've probably already been looking at that. First one, they use the arctangent rule at u equal x and a equal 3. And then this integral of 4 over x squared plus 9 dx is the same as 4 times the integral of 1 over x squared plus 3 squared dx, exactly like we did. And that gave you 4 times 1/3 arctangent or inverse tangent of x over 3 plus c, which would be 4/3 arctangent x over 3 plus c, just like we did. The arctangent rule does not apply to the b part because the numerator contains a factor of x, so consider the log rule. Okay, let u equal x squared plus 9, which is exactly what we did. Then du is 2x dx. So we had 2 times 2x, that's your 4x, dx over x squared plus 9, which is 2 times du over u, which is exactly what we got, which is 2 times log u plus c. Go back and put in what u is. U is x squared plus 9, so that would be 2 times log of it. And because x squared plus 9 is always positive, you can lose the absolute value bars. X squared plus 9 plus c. Make sense? Got a hiccup, sorry. Now, something to keep in mind. The log only operates on this in parentheses. It's not x plus 9 plus. If you left off the parentheses, you would think the 9 and the c go together. They don't. These parentheses say that's what you take the log of, and then once you've done that, add c to it, whatever, that's your integration constant. All right. And then the c part is because the degree of the numerator is equal to the degree of the denominator. You should first use division to rewrite the improper rational function, sum of a polynomial and a proper rational function, and that gave you 4 plus the, I don't know why they say plus. I would have said minus 36 over x squared plus 9. Whichever way works fine. So the integral of 4 dx minus 36 times the integral of 1 plus that dx, 1 over x squared plus 9 dx. That'll be 4x minus 36 times, and then that goes back to the inverse tangent rule, and be 1/3 inverse tangent of x over 3. Well, that's going to be 1/3 of negative 36 is negative 12, so 4x minus 12 inverse tangent of x over 3 plus c. And again, this time without the parentheses, the arctangent operates only on the thing immediately after it, not there. For to operate on both of those, you have it in parentheses. That's not what you have. It's just operating on that. So you operate on the previous one, whatever's in the parentheses, not what's outside. Without parentheses, you operate just on what's next to it, and don't use the plus to try to tie that in. Okay. Now, they're skipping example 2 and 3 and 4 and 5 and 6. All right, and here's this. Pardon me?
That's a lot of examples. I wonder why they skip it.
I'm sorry, I can't hear you.
That's a lot of examples. I wonder why they skip it.
I don't know. I do not know. It's sort of a mystery to me. They usually will do the easy ones and skip the harder ones. So let's go back and do okay. This has the most white space, so let's do example 2. This is acting strangely. Example 2. Evaluate this one. This is a definite integral, 0 to 1. X plus 3 over the square root of 4 minus x squared dx. What would, let me look this out again, because since you're here, you may not go back and listen to the first part on YouTube. I need research papers in this week, right? And I need all your previous tests in this week. Now, the one I gave to you last week, if you need another weekend to work on it, that'll be fine too. I'm going to give you your final exam, which is just going to cover what we cover in Chapter 8, which we're not making great progress, but we're going to just what we covered here. That will be your last test. And it will be fairly short and sweet, hopefully fairly easy, okay? But the I need the rest of them, test 1 and 2, in this week if possible, so I can get those back to you on Wednesday. Okay, so get them to me if you can. And since several of you came in, I forgot to say this. If you haven't done the student course evaluations yet, those are out there and open, right? Okay, so please do your student course evaluations before you leave for Christmas. Okay. So, what would be your approach here? Anybody? What would come to mind?
Getting the square root out of the denominator.
Okay, what about the denominator?
Getting the square root out of the denominator.
Oh boy, it's a big order, isn't it? Here's what I think is better. Let's first split that numerator into 2 pieces, okay? And then so this will be the integral from 0 to 1 of x over the square root of 4 minus x squared dx plus 3 times the integral from 0 to 1 of dx over the square root of 4 minus x squared.
Would it have been easier if I would say using the substitution to get rid of it? Or?
Okay, substitution on that first will work. So that's what we're going to do. We could have tried substitution here, but then you still have the mess up with the 3 here. You'd have your x up here, because this will have an x in it, but you don't get a plus 3. So it's actually a little easier to split them into 2 pieces. This one, which is substitution, will work well, and And that one we're going to have to look at some of the other integration rules, one in particular. We'll get to that in a second. Let's do this one first. What's your substitution would you use here?
U equals 4 minus x squared.
4 minus x squared. Perfect. Then du is equal to
2x
minus 2x dx. Perfect. And you have an x dx there, so let's divide both sides by minus 2, and that will give you minus 1/2 du is equal to x dx. Okay. Now that integral up there becomes the integral of the, and let's pull the minus 1/2 out front. Minus 1/2, that's from the du. Du, because x dx would be du with that minus 1/2 out front, over what? Yes, u to the 1/2. Okay, which I would prefer to write as minus 1/2 times the integral from of u to the minus 1/2 du. I never like to divide by radicals or by things in the denominator. Bring it upstairs and put a minus in front of it. Now, one thing we haven't done, changed our limits. Okay? X is going from 0 to 1. So when x is 0, what is u? 4. So that would have me a 4 down here and down here. And when x is 1, what would that have me? 3. Second?
Oh, yeah,
3. Okay. U would be 3. So that would be 3 here and 3 there. Well, I sort of don't like having a bigger limit on the bottom and larger and smaller one on top. How do I correct for that? Anyone remember that rule? Change the sign of the integral. So it changes from a minus to make it a plus 1/2 from 3 to 4 of u to the minus 1/2 du. That's going to be the new integral. Okay. Now, still going to be a little messy. Let's go on and do that integration. What does that give you? It's just a power rule. What does that give you? 1/2 Did I hear a u? Maybe I was imagining it. U to the?
negative. Would be u squared over 2.
No. Okay. Let's go back to the power rule, which I think you all know. Number 4, u to the n. N doesn't have to be an integer. Any value whatsoever. What's n plus 1? In this case, minus 1/2 plus 1. U to the 1/2 over, which is same as dividing by 1/2 is the same as multiplying by 2, and that'll wipe out the 1/2 there, won't it? Okay? And this will be evaluated from 3 to 4. Now I can do the first part. 4 to the 1/2 would be 2 minus the square root of 3. I can't do anything with that. So that's the first part. the first integral. Let's go to the second integral. What does that look a lot like? Plus 3 times the integral from 0 to 1 of, well, maybe I shouldn't have even put the integral here, just put the 3. And what does that look like? It might be the integral of. Look a lot like number 18, and that would be the inverse sine of my u's and the x's are exactly the same, so that would be x over maybe it would have helped to have written this as integral from 0 to 1 dx over the square root of 2 squared minus x squared. X over, in the book 18 is the square root of a squared minus u squared. Here, x over 2. It's a, not a squared. Right? Oh, I left off the in front. Okay. It's 1 over a. I'm sorry. It's not 1. I didn't think it was. Okay. It's just inverse sine of u over a, which is u over 2, x over 2. But we're evaluating that, if I could get my pen back, evaluating that from 0 to 1. Okay? So it's 3 times, what's the inverse sine of 1/2? Okay. Okay. Let me write this down. It's inverse sine of 1/2, and we'll do the same minus inverse sine of 0. Okay. Now, what this means, you take the sine or any trig function of an angle, you produce a number, right? When you're taking the inverse trig function, you're taking that of a number producing an angle. Okay? An angle could be either in degrees or radians. Let's stay in radians probably. So what angle, that's what inverse sine is saying, what angle, when you take the sine of it, do you get a 1/2? Yeah. And your calculator will do an inverse sine of 1/2. Yeah. But it'll give you a decimal number, which you probably won't recognize. Huh?
Well,
oh,
degree
okay.
mode, so that's 30 degrees.
Yeah, in degrees it would be 30 degrees. How many radians is that? How many radians? Huh?
Pi over 6.
Pi over 6, exactly. So that would be 3 times pi 6 minus, and what's angle, if you take the sine of it, will give you 0.
Pi halves?
No, that will give you 1. Sine of pi halves is 1.
Oh, so it's 0.
0! Okay, so that's 0. I was going to volunteer to do that, but I thought maybe you needed to. So this becomes pi halves. So this one was, the final answer is 2 minus root 3 plus pi halves. believe that's it. Nope. Yeah. Believe that's right. So let's see what they got here. Goodness, what a weird way to do the answer. They say minus 3 plus pi halves minus a minus 2, which is plus 2. So that's exactly the same answer we've got. They actually did the math on it and rounded. Square root of 3 is an irrational number. Pi halves is an irrational number. Rounded to 3 decimal places or 4 digits, they say is 1.839. I haven't done that. I'll let you do that and see if you get the same answer. Okay. And they say the midpoint rule can give you a good approximation. Where in the world are they coming from here? That's not quite the same problem. They're doing 0 to 1.99, which is not 0 to 1, it's 0 to 2 approximately. So I'm not quite figuring out what they're doing there. So forget that technology bit there. I don't see what they're doing. If that is indeed the case, for n equal 5, the midpoint rule gives an approximation of 5.667. That's pretty far off from 1.839. I have a feeling that little technology blurb was in from the previous edition, but they changed the previous problem, so don't worry about that. That was bizarre. Again, rules 18, 19, and 20, the basic integration rules for preceding, all have forms of a squared minus u squared, or a squared plus u squared, or u squared minus a squared in 18, 19, and 20. Some with square roots and some with not, some with other things. So that's just a bit bizarre. So let's do example 3. Let's see if we can do that just using what we know here. Okay. Find the integral of x squared over 6 square root of 16 minus x to the 6. And then we'll have a dx plugged out here. Oh man. All right. Rather a bizarre kind of problem here. It doesn't fit any of the things on the table there, review of basic integration rules. The thing that comes closest to is, and it's not really all that close, almost like a 20, but not quite.
I mean, we can take the square root of 16 and break it down to like 4 squared, right?
Second?
I see we can break down 16 to 4 squared, and that'll give us
Right.
we got 8 squared. How would x?
Okay. Here's where I think our answer is going to come. Let's rewrite that denominator. See, it's not quite the same as 20. It's a little more like 18, but not quite like 18 either. But let's try to work with 18 for a minute here. And here's what I'm going to do. The integral of, and it's kind of a backhand substitution. Let's let u equal, how about u squared equal x to the 6th. How would that be for you? Which implies that u is equal to x cubed. Okay? Now, that's the same thing, right? Then we'll have a denominator that looks more like 18, right? A little bit, right? Okay. So if u is equal to x cubed, then what do we do next? Du is equal to 3x squared dx. Hey, hey, hey. We don't need 3x squared dx. We wanted an x squared dx, and look at what we've got. So let's divide both sides by 3, and you've got it. Okay, the 3's go out here. Now, this is not a definite integral. Okay, so we'll leave it indefinite here. That would be 1/3. That's where the 1 over 3 went. Okay, and this will be du x squared dx over the square root of 16 minus u squared, right? Yay or nay? Got it? Make sense? Okay. Now, that looks, buddies, just like, or very similar to 18. Okay? So this will be a 1/3. That's already there. The integral of du over the square root of, what would that 16 be in terms of a square? 4 squared minus u squared. And I think we can go to town with that one. 1/3 of what? Using number 18. Say again?
1/3 of arc sine first, right?
I still couldn't hear you.
Doesn't arc sine come first? Though?
Oh, you're absolutely right. I'm sorry, I was looking at arctangent. Okay. Arc sine of, inverse sine of, what? Yeah, we'll go back to that. U over 4. Got it. Plus C. Okay. Now let's go back and plug in what U is. U is, or U are, x cubed. So it'll be 1/3 inverse sine of x cubed over 4 plus C. 1/3 arc sine x cubed over 4 plus C. Got it. Make sense? All right.
Is there any way to solve that one?
What do you mean solve it?
Well, oh yeah, I guess you can just plug in anything for x because it's indefinite.
Well, you mean find out what C is? Is that what you mean?
Oh no, I meant just like how on the last one we were able to come up with pi over 2.
Okay, the part of that was because that was a definite interval. Yeah, and this is indefinite, so that's why I said you'd be trying to find something that C was equal to. That's what we were doing before. It's kind of. Okay, so that was example 3. Let's move on to example 4. All right, to erase?
Running down.
Oh, you're still getting, okay. Got it, everybody? Okay. All right. Now let's erase this, if I can find mine. There we go. And let's go to example 4. I don't know why I'm suddenly so hungry I can hardly stand it. Okay. Here's an integral. 1 over 1 plus e to the x dx. What might we do there? What's that?
I was checking to see if it was similar to one of engagement rules.
Yeah, yeah. You can look, but nothing exactly like that exists there. So what might you try?
Substitution.
Why not? Okay. So what would you want to substitute?
DU.
Let u equal what? 1 plus e to the x. Then du is equal to is what?
I was saying XE. I'm trying to think of XE.
This isn't power rule. This is the exponent rule. What's the derivative of 1 is 0. I took care of that one. What's the derivative of e to the x? My favorite of all time. E to the x dx. Okay? Now, sort of doesn't seem like it's helped us a lot, does it? Okay?
I mean, there's a 1. I see a 1 in the numerator and 1 in the denominator, so I thought those may have. No, it's still like the previous problem. So, like you said, it didn't help us much.
Okay? Don't think that's going to help us much at first, but let's see if there's anything else we can do. I don't think there is. That was a good effort, but didn't produce much. Okay? But let's see if maybe let's take this e to the x that we wound up with here and say e to the x e to the x is equal to u minus 1, right? Okay, so then that would be u minus 1 dx, but let's get the u's over here, so you would have du over u minus 1 is equal to dx. That was some sleight of hand, wasn't it? But was it legal? In most states, I think that's still a legal thing to do. So let's see then what we've got. We've got a over u, that's 1 over e. The first part here is 1 over u. And the second part is that. So it seems like that becomes 1 over u times du over u minus 1. Okay? Which would be the integral of, and these are indefinite integrals, which allow us to do this kind of stuff, du over u squared minus u. I don't know. Are we now in worse shape than we were to begin with? Or maybe I shouldn't have multiplied those two together. Oh, clever them. Yeah. I think we could get there this way, but they got there an easier way. So let's go back and do it their way. Okay. I forgot this little trick. Okay, sorry about that, folks. This is a weird way to start this chapter. Okay, I've never seen a book do this. Here's what they're going to do. Strange but true. In that numerator, 1, and this may be what the markers was talking about, let's add an e to the x and subtract an e to the x from that 1. We haven't really changed the 1, it's still 1, right? Okay. And put that over 1 plus e to the x. And here's our dx out there. This is what was clever about the way they did it. Okay? Now, let's split that into two integrals. The first one being the integral of 1 plus e to the x over 1 plus e to the x dx minus e to the x dx over 1 plus e to the x dx. Oops. You don't need another dx in the denominator. Okay, sorry. See what they did? They added an e to the x and subtracted e to the x. Why did they do that? So they made this look just like this, which gave them this, and then the second integral is minus e to the x over 1 plus e to the x dx. Now, what is that first integral? What is this? 1 plus e to the x over 1 plus e to the x. That's 1. I think we can all do the integral of 1 dx. What's that? X, okay. All right. Minus. Now we do our substitution. I knew we were going to have to somewhere here, and here's where we do that. And it was exactly the same one you did before. Let u equal 1 plus e to the x. Then du is equal to, remember what we did? Second? E to the x dx. And that's exactly our numerator. So that'd be minus the integral of du over u. And what's that? What's the integral of du over u? Third time today. Log of u. But what is u? What are you? I don't know what you are. Okay, what is that? U is 1 plus e to the x minus log of 1 plus e to the x. And by the way, e to the x is always positive. So 1 plus e to the x is always positive, so you don't need your absolute value bars, and then you do a plus c. And that's the answer. Got it? Yay or nay? See how we got that? Okay. Okay.
Time flies when you're having fun.
Is it time?
Yeah, 10, about 8 minutes.
Huh?
Got about 8 minutes.
8 minutes, yeah. Okay. All right. People still writing here. Yes. I'm sorry.
I say, am I the other one?
No, everybody got it? Okay. I thought Daniel was still writing too. Okay. All right. Let's close this out and do example 5. Whew. Talk about some weird ones. The integral of cotangent x times the log of sine x dx. Now, the first thing in my book is I don't like messing with cotangent x at all. Okay? So how would I write that?
1 over tangent.
You could, but I really don't like working with tangents that much either. If I can get everything in terms of sines and cosines, I'm a happier camper.
Oh, so it would be cosine over sine?
Yes, exactly. So let's try that. This may not be the way to go, but this is what I would try first. Cosine x over sine x times the log of sine x dx. Okay. Now, anything come to mind here?
The log of sine x is not equal to
The integral of 1 over sine x is log sine x, right? Is that what you're thinking?
yeah,
That's exactly what I was thinking. Okay? So, let me think. What we have here is the integral of cosine x times 1 over sine x times the log of 1 over sine x. Well, the integral, like you say, of 1 over sine x is log of sine x. So we don't have much time. So let's get right to the chase here. They said, let's let you, I probably should put it over there. No, here, that may be too confusing to put it here. Okay, let u equal the log of sine x. Then what's du?
we just talked about being 1 over sine x.
Perfect. Times, chain rule, You got the log part. You took the derivative of the log and went over to this, and then the chain rule says take the derivative of that. What's the derivative of sine x?
So, cosine?
Cosine x. Okay, and that would be a dx then. Look at what we got. We got the integral of u du. Because this right here is du, and this part right here is u. And what would that give you? Anybody? Fairly simple little power rule, right? U won't be u, because derivative of u would be 1, not u.
Squared
Over 2. Okay? Plus c. But then we plug in what u is, which is log sine x squared over 2 plus c. And that's about all we can do with it. And we've got it done. All right. Can we squeeze one more in, or are we through? What we got?
2 minutes, but I'll stay.
Huh?
I said we got 2 minutes, but I'll stay.
Okay. Let's see if we can get this next one done. Oh, y'all need to finish writing that one down.
Are you going to teach Cal 3 next semester?
Yeah, planning to anyway. Yeah. It's on the schedule, I hope. I put it there. I can't remember when. It's on a Monday and Wednesday. I'm guessing early afternoonish. Okay. Everybody finished getting this one? Yeah or no?
Yeah.
Yes? Okay. Want to try to get the other one, or we use our time up?
Let's try to get the other one.
Huh?
Let's try to get the other one.
Okay. Let's do example 6 really quickly. All right. Example 6 is find the integral of tangent squared 2x dx. Okay. Now this is no, it isn't. I thought it was going to say this one almost seems like a fairly easy one, but it's not nearly as easy as I thought it would be. Okay. It uses a Pythagorean identity. What is tangent squared in Pythagorean identities? Tangent squared 2x is equal to, I'm going to write it over here. Anyone remember that Pythagorean identity? Tangent squared 2x is, it has something to do with secant squared. Let me write it this way. Tangent squared 2x plus 1 is equal to secant squared 2x. Agree with that? Because sine squared x plus cosine squared x is equal to 1. And if you divide both of those by cosine squared, you get tangent squared plus 1 is equal to secant squared. But now it's 2x. Okay? So let's change this to the integral of secant squared 2x dx plus the integral of dx. 1. Yeah, blah, blah. Okay, secant squared dx, that was in our table, right? Number 14. okay? Except that silly little 2x there is messing us up a little bit. So let's let u equal 2x, then du is equal to 2dx, and 1/2 du is equal to dx. Okay. All right, whatever. So now we have the integral of secant squared u, 1/2 the integral of secant squared u du, right? All right. And what's that? That is directly off of here. Secant squared, number 14, that'd be 1/2 tangent u plus c. All right. But we need to go back and plug in what u is. That's 2x. So that'd be 1/2 tangent of 2x plus c. But let's do the other integral. And this integral is x plus c. So we don't need 2 plus c's. So our total thing is 1/2 tangent 2x plus x plus c. Whoops, how'd they get a minus? Oh, sorry about that. Tangent squared, I set this up but I didn't carry it out. Tangent squared 2x is equal to secant squared 2x minus 1. So that's now a minus dx, and this would be a minus x here. So yeah, that's what we got. 1/2 tangent 2x minus x plus c. All right. We'll start next time with, I'm just going to get this set up for us. This table here. Procedures for blah, blah, blah. Fitting integrands to integrand rules, which is what we've been doing, but we're just going to hopefully simplify it a little bit. Homework exercises here. Basically, we've done all the examples. We've just got to go through those procedures. Do number 3, it's at calcchat.com. Any of the odds 5 through 13, they're at calcchat. 7's at calcview. Any of the odds 15 to 45, and they're all at calcchat. 17's at calcview. Do 47, it's at calcchat. Do 49, it's at calcchat. Any of the odds 51 to 55, they're at calcchat. Any of the odds 57 to 71, they're at calcchat. 59's at calcview. 73 or 75, they're both at calcchat. 77 or 79, they're both at calcchat. You can look at 81 if you think about doing it. If you want to, it's up to you. It should be at calcchat, but if it's not, forget it. 83 and or 85. Or it should be at calcchat. 87 should be at calcchat. 89 should be at calcchat. And then any of the odds 91 through 95, they should be at calcchat. 97 should be at calcchat. 99 should be at calcchat. And you can look at 100 or 101. I mean 101 or 103. It's up to you. And we'll go back and look at that table of procedures. We'll start there next time. And then get into the real part, in my mind, of this chapter, integration by parts, which is a fun thing to do, and we'll get moving on that too.
I have a question.
Yeah, okay, I thought you had a question, yeah.
Are you still passing the other test out?
What's that?
Are you still passing the other test out? The final.
That'll be Wednesday, yeah. I'll be doing that, yeah. I want to see how far approximately we get before I make it out, so, yeah.
You know, I've talked to you earlier about changing my major maybe to some form of teaching.
Right.
And would I still need Cal 3 if I was going to be a math teacher?
Ultimately, probably so. I don't know if it's on the degree plan here or not, but I can't remember what that is. But I would think so, but I don't know. Because to be a math major, you're going to have to do all your calculus, whatever school you go to. So It should be on the degree plan. I can't remember. And they've done some changes to the degree plan too, so I can't say for sure.
Okay.
All right, you too. Thanks.
What time do you usually get here on Wednesdays?
A little before 8.
Do you think that I can meet you in your office about 8 o'clock on Wednesday
Sure,
morning?
I think so. Yeah. Now this Wednesday I might be a little later than normal because every other Wednesday is the day our cleaning lady comes, and we have to clean up for our cleaning lady to get there.
I know
So
how that goes.
I've never quite figured that one out, but so there's certain things we got to do. It takes a little longer, but hopefully I'll be here before 8. But if not, I'll be there shortly thereafter.
Yes, sir. All right.
But it just happens to be this is every other Wednesday. Right. Okay.
Thank you.
All right. Did you get the last test?
Test 3?
Yeah.
Yeah.
You did.
I got one more question.
Okay. All right.
I haven't been up on Wednesday.
Okay.
And, what was your email again?
My email,
Yeah.
cfiler@lawsonstate.edu. First initial, last name at lawsonstate.edu. That's most of us. A few of us have something a little different, but most of us are that. Employees, when I say us.
Now it popped up on my phone. That's crazy.
What did?
I was using my iPad. I had just had my iPad with me at work, and I left my phone in the car, and I was trying to email you the paper,
Right.
but it wouldn't give me the address.
Right.
And when I just did it on my phone, it popped up.
Huh.
Like you know how the contacts are usually
Right.
saved when you do the
Right.
school one? It wouldn't do it on my iPad. Maybe it needs to be updated too.
Yeah. My wife has trouble sometimes getting her phone and iPad to get on the same page, so to
And
speak.
I was like, usually it pops up, so I couldn't figure out what was going on.
Yeah, I don't have an iPad. She does, but
They're cool if you can figure out how to sync everything.
make them to work the way they should.